In this work, we present Guiro, a visual analytics system for user-guided matrix reordering. Let us first explore the question of why I should care about matrix reordering. Matrices are powerful visualization techniques for network data with three outstanding properties. First, in the simple yet effective row and column layout, every pixel can contain information about the underlying relational dataset. Thus, matrices reach their scalability limit only if all screen pixels are occupied. Second, unlike node link diagrams, matrices do not suffer from overplotting, making it easier to explore large networks. Third, the feature that makes matrices an interesting research topic is that they allow the analyst to see, overview, and detail in one plot. Just by looking at the size and visual density, we can estimate the network size and amount of network connections. However, if the row and columns of the matrix are appropriately ordered, then we can see the topological details of the networks. Now let's see who uses matrices. We designed Guiro to help general users find the correct and most expressive matrix reordering. In other words, the one row and column layout that makes visual patterns emerge. In every information visualization lecture, we teach or learn that matrices can be reordered in many ways. With Guiro, we make this explicit. In our web-based system, the teacher can invoke 70 distinct matrix reordering algorithms from several matrix reordering algorithm classes, such as classical hierarchical clustering or optical leaf ordering approaches over spectral algorithms to graph-based approaches, such as TSP. Additionally, we can compute 16 quality metrics. In this view, we are showing only the two most important ones. Another concept is more important. Guiro helps us to understand whether or not an algorithm is heuristic. In other words, if its results can be validly reproduced. All algorithms can be applied to the matrix for a further analysis of the underlying data. This brings us to our second and primary user group, the network analyst. Typically, network analysts have different needs and also a more profound level of visualization literacy. In other words, they have a good understanding of how the visual patterns need to be interpreted. However, when analyzing network data, we all have already experienced that our algorithms either produce aesthetically pleasing results or results in which certain parts expose a visual pattern, while the other subparts are cluttered. The reasons for this are simple. The algorithm was designed to be effective for a certain visual pattern, while the algorithm cannot grasp another pattern. In Guiro, we help network analysts with two novel interaction mechanisms to understand what matrix reordering algorithms are doing and to steer them in locally uncertain areas. We make use of a projection view for this purpose. Here, the 2D nodes represent the higher dimensional counterpart in the matrix. The idea is simple. In a good projection, similar row and column vectors will be projected close to each other. We can now represent a reordering result as a Hamiltonian path connecting all the nodes. Put more simply, whenever the nodes share a link, they are also next to each other in the matrix. On top of this concept, we allow the user to modify direct adjacency relations of the matrix rows and columns. This interaction is similar to drag and drop reordering of rows and columns. The second interaction technique allows the user to select submatrices and apply totally different matrix algorithms locally. By letting the user apply a different reordering algorithm to this local submatrix, we can also make patterns visible for which the global algorithm was not designed. These two powerful interaction tools allow us to apply a global reordering on the matrix, such that the main patterns or topology can be seen. But then our focus on analysis of subparts of the matrix, which are either of particular importance or just not well represented by the global algorithm. The third target user is the algorithm designer. Let's imagine for a second we want to publish a new matrix reordering algorithm. In each and every paper that we want to publish in a conference, the reviews expect the comparison to be state of the art. Not only is it challenging to gather all the algorithm implementations, but also we have to implement all the necessary evaluation metrics. In Guiro, we make these kind of comparisons first class of every matrix analysis. The web-based system allows not only to upload our own dataset, but also to compute 16 quality metrics for every matrix reordering result. Additionally, we allow algorithm designers to understand the differences and similarities of matrix reordering on a pairwise similarity level. In parallel coordinate plots, we show reordering results in columns and connect the rows and column vectors with respect to the index position. This plot is inspired by Wilkinson's grammar of graphics, which suggested to use Spearman's rank correlation to compare linear arrangements of matrices. By dragging and dropping the parallel coordinate axis, we can change our comparison subjects. Here, we can find that two algorithms have two entirely same matrices ordering the results, although they have different implementations. Guiro has another interesting evaluation tool for algorithm designers. We can show how we can modify the projection of every dataset and matrix reordering algorithm to show a 1D projection, similar to the plots depicted by Diaz in his survey of graph layout problems. With this projection view and edge encoding, we can even understand why certain quality metrics such as linear arrangement or minimum cut come to their conclusions. We evaluated Guiro's usefulness and understandability in a guided explorative user study with several subjects. We found that our proposed methods help even inexperienced users to reason in matrix pattern spaces and allow an educated, user-guided steering of reordering algorithms. In summary, Guiro is designed to answer 3 recurring research and analysis questions. First, which matrix reordering algorithm should I choose for my current analysis question? Second, which local patterns are hidden in my data and cannot be found with global algorithms? Third, how can algorithm designers develop even better algorithms? With Guiro, our goal is to increase the transparency of matrix reordering algorithms, thus helping a broad range of users to get better insights into the complex reordering process, in turn supporting data and reordering algorithm insights.